shining as the world wakes again. Hey, mister, can you tell me, does space bend? All around you is the sound of laughter. Joyous people celebrate a life so grand. Hey, mister, read that fairy tale again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. A gentle breeze blows across the ocean, sending waves that crash upon the sand. Hey, mister, did you watch Slow Down again? There is time for you to smell the flowers, even though the thorns get in the way. Hey, mister, what's your theory for today? Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day.
Oh, come on outside, ladies and gentlemen, boys and girls. What you're about to see is out of this world. Step right up now, don't be shy, because we're about to show you how cars can fly.
Here's a tale of a suburban housewife who dares to fight with the icon of his day, and she finds her own miracle on the way. I said, hey now, life's a joy. You gotta try your best and give your all, and when the facts don't fit the theory, change the facts again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. It's a beautiful day.
5, 4, 3, 2, 1. Silence. Good morning, good evening, good afternoon, wherever you are in the world. I know people are watching from around the world. In fact, our people on the west coast of the United States have it the worst because they have to get up the earliest, but I do like that time because we get people from all around the world. And today we have a fantastic show. One of our Lifetime Achievement Award winners from the CMPS, Dr. Gerald Pollock, on the fourth phase of water. We have a lot of new people in our organization, and I know a lot of people have seen him before, but there's a lot of you who haven't, and he has been so gracious to join us this morning very early. But of course, we got some things to take care of before we bring him on. Yes. And of course, we are the John Chappell Natural Philosophy Society and also Dissident Science. I want to welcome all of our subscribers. We've got over 4,000 subscribers between both of our channels. In fact, John Chappell Natural Philosophy Society is growing and should reach about 1,000, which is great because you reach 1,000, there's all kinds of things that can happen. Of course, I want to thank all of my my subscribers from the Dissident Science YouTube channel. We're heading our way to 4,000 subscribers, and I want to thank all of you. This is a very unique place, of course, and that's why you're here. And of course, I want to thank everyone because everybody who listens to this is supporting people who are working outside the mainstream, who are doing fantastic work. And as we all know, the people outside the mainstream are the ones that push science forward. If you're in the machine itself, you're not going to go very much take science forward. And of course, our guest today is a great example of that, who is actually moving science forward in an amazing way. So again, he's coming up, Dr. Gerald Pollock. But I want to thank everybody for all their support, everybody who tunes in, everybody's watching this unrecorded, because we get most of it is watch after it happens. But of course, the live version, it's really great because you can come in and join. We have up to 10 seats in our green room. room, so you can come one-on-one with our guests if you want, talk to them face-to-face, or you can also put something in the chat, and we can throw whatever's up in the chat on the screen and talk about it too. So, and of course, we are where critical thinkers meet. The John Chappell Natural Philosophy Society provides an open forum for the study, debate, and presentation of serious scientific ideas, theories, philosophies, and experiments that are not commonly accepted in mainstream science. The CNPS uses the term natural philosophy in its broader sense, which includes physics, cosmology, mathematics, and the philosophy of science. Our goal is to return to the basics where things went wrong and start anew. That's for sure. Oh, I got this. Take the branding off, Dave. Yeah, we're still learning to use this software. There we go. But let's keep moving. Why are we different? Well, we are an organization that above all promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside the mainstream, to provide a forum for open debate about modern topics in physics, cosmology, philosophy, and mathematics, to provide a forum for presenting serious papers and theories without fear of censorship. And of course, we are run and controlled entirely by our paid membership and the election of instructors by its members. So we are a member organization. I had to make these slides all over because my hard drive with all the slides I gave to somebody and realized all my slides, so I had to make these all over. So I apologize for anyone who's seeing this every week. But of course, those people who are new haven't seen this, and that's why we do this every week. So who we are, of course, we are open to challenging mainstream science. This is more of an informal way. We allow and encourage competing ideas or models. Heaven forbid that. I mean, my goodness. Unfortunately, you go to universities and you are basically told what truth is, but we don't believe that's really the way to teach. And of course, I know our guest today also believes that's the same thing. And we do follow scientific method. I think a lot of times people think when you challenge or mainstream science, or you come up with a new model, that you sort of like throw everything out. I don't follow Newton. I don't follow, there's no graph, no, we follow the scientific method like anybody else. And we also can, as Aristotle said, we can consider an idea without accepting it. And that's really, really important. If you want to be a true critical thinker, you really need to do that, because if someone comes up with a new idea and you go, they start talking and it goes against what you think the way the universe is, and that's not a great attitude, because exactly that person who you think is crazy and that idea is just too far out, maybe the next person who's changing science for the better and advancing science, it's not going to look too good. So please try to keep that attitude. It's one of the things we try to teach here. And of course, we give voice to the voiceless, and this is where mainstream advances. I mean, in the end, this is where mainstream advances. It's not inside the mainstream, it's actually outside. Who we are not. We don't have a specific point of view. That is, we have people that have conflicting points of view. So a lot of organizations have specific points of view. I'll give you one. I really love that organization, the Electric Universe. They look at the universe much more as electric, and they have a lot of things that people sort of subscribe to that are much more in common. We don't do that. We have people who are Electric Universe. We have people who are Newtonians. We have people who all kinds of different points of view. So that's important for our organization. Of course, we're not also a general science organization. That's not our goal. We're not here to teach people what's already sort of known. We already have enough of that. So, and we're not sort of new age, sort of this, a lot of people are into what we call science poetry. We're not really into that. Conspiracy, UFOs. Hey, everybody, a lot of conspiracies end up being true because people who don't want those things to come out, they will come out. But again, I think this last statement is really important. We stick to the foundational science. Let's try to figure out what light and gravity fields are, and magnetism, tectonics, math, philosophy, Big Bang, is that real or not, relativity, all that kind of stuff. We've got so much on our plate. We really just don't have the time to do and look at, things like conspiracy and all that. And of course, because I made these slides, I've got a repeat slide here. This is what it's supposed to say, mission. So on to the next one. We do have some websites, Science Woke. We're going to be talking about that actually and shortly before we bring our guests on again. I thank everybody. If you came here to listen to Dr. Gerald Pollock about the fourth phase of water. He is coming with a shorty. I see him in the green room, and he's waiting the wings. So we do have Science Woke, which is really an online magazine for critical thinkers. It's really a great place to start if you're not really a technical person. It shows you all the problems in mainstream science and gives you a lot of the people who are the critical thinkers there who talk about things. I'm pretty sure Dr. Gerald Pollack's there too. And you can check him out and all the other critical thinkers out there who are moving and shaking the world in a positive way. We also have, of course, our critical thinking community at naturalphilosophy.org. And that's a great place. You can join us in joining the really stimulating discussions. Brand new software out, Buddy Boss, it's called. It's really great. Sort of like social media meets a regular website, and it's really great. So check that out. Register, get involved. And of course, we have our Wikipedia, Natural Philosophy Wiki, and that's at wiki.naturalphilosophy.org. And we have over 10,000 pages there. And that really came from our database. And of course, Wikipedia doesn't take kindly to anybody who says the Big Bang's wrong. You don't go to the Big Bang page on Wikipedia and see all the arguments against it. They don't do it because Wikipedia, what is it? It is by nature consensus. So if it's consensus, you're not going to find anybody out there who is challenging. So check out our websites. And interesting enough, we just actually, Nick Percival, who is one of our great scientists of our organization, but also a director, brought up a point which I really knew about, and I just didn't bring this to light, but we do need to deal with it, and that's giving Science Woke Online Magazine a new name. Unfortunately, in linguistics, I've got a master's in linguistics. That's one of my areas. I work with computers and human language. Unfortunately, words can be hijacked and bad connotations given to them. The idea of woke was really a simple idea that as a person says, oh, what I didn't see before, I now see. Oh, I thought that, of course, we needed to get into this war or we needed to do this. And you find out, oh, maybe there's some other motivations for doing that, like money and power and things like that. This idea is in my opinion, was a very positive one. And a number of years ago when we started sciencewoke.org, that was the idea. But unfortunately, some people took it because the people fighting amongst themselves is a very powerful way for the powerful to keep us in check. And of course, I'm not here to talk about politics. Everybody's got different politics. In fact, our organization doesn't talk about politics. And I have lots of friends who have completely opposite political views, but we're still great friends. But the thing is that Science Woke on one side or the other got a bad connotation. And so we are looking for trying to rename that website. Unfortunately, we have to do that. If you don't know what that all means, well, take this, for example. And when I was in linguistics, we learned all these stories about society and language. Take the word retarded, for instance. Oh, that's retarded. Well, it turned out that retarded, when it first came out in, I think, the 1950s, was meant to be a neutral word for people who had disabilities, is what we say. But what happens in society, you can't change people's outlook on it just because you change a person's word, the word for it. Then we went to even special. And now if you hear kids today goes, oh, you're really special, it's now become a derogatory word. So unfortunately, words can change. We try to be in up to date, the idea of Science Woke. So what I would urge everybody to do is go to naturalphilosophy.org. We have this new group giving Science Woke Online Magazine a new name. You can see there's some text here, but join in, give us some suggestions. Critical thinker is one of them, but it's not it could be. We did have actually critical thinkers info or something like that. I don't know. But anyways, we do need to rename that. It's called rebranding. We're going to have to do all our logos and all that stuff. But we think it's important enough because I actually had one scientist who said, I don't want to be in it anymore because I'm woke is a terrible thing. It's like Nazi or I don't know. So things change. You got to adapt, just like we're here today, doing these live broadcasts and staying up to date. So please put in your 2 cents worth if you have any ideas of what we could actually call it, because it's all in the end, it's really it's an online magazine for critical thinkers. That is the tagline. It shouldn't really change in this sense because that's really what it is. But what will that name be? And I know a lot of people would have, and I told Nick, I said, let's just open this up. So he made that a private group, but I made that public this morning. So you should be able to join and put in your bids for it. Bids. We don't have a prize for it. The prize is you'll be happy. You'll be the person to, maybe we'll put the person's name in it in the about or something like that. But anyways, we need your help. Please take a look at that. Also, we do have memberships, and I want to thank, we got a silver membership, annual membership. That's $100 a year. We have a couple monthly memberships people are paying, $5 a month. If you are on a fixed income, it's only like $60 a year. But we have literally thousands of dollars that we need every year to keep us going. Why? Well, we have a server, and that server needs $200 a year so we don't get hacked because of what we do. People want to hack us, and they have done that. And so we have a company that makes sure that people can't come in and destroy our database, which we've had happen numerous times. We have it backup. I have it backed up on my computer, and that gets backed up into Carbonite. We also have all the Buddy Boss new software. The membership software. It's no longer software I wrote. I wrote over a 10 years period of time. I wrote a bunch of proprietary software that we use. But of course, if I decided to go away, then how could we do this? So now we have all the software, which is all commercial. We have LearnDash for also making online courses. So all those things cost a couple $1,000s a year. So your contributions, both monthly and annually, are very much welcome. You just go to our website and look under members, and you will see a button there for paid memberships and donations. And I want to thank people who do make donations. And we do have patrons, what I consider patrons, people who have given some significant money to our organization. And Dr. Cynthia Whitney, who is our chief scientist. I always lose these names. Our chief something scientist for our organization. She's the top scientist. She's got her PhD from MIT in special relativity, and the first job she had was to apply it to a ring gyroscope, and guess what? It failed. And what happened? She became a dissident because she realized special relativity doesn't work. In the very first thing, went back to her professor. Professor said, she said, hey, professor, I just got my PhD in special relativity. I applied to the ring gyroscopes, and it's not working. Professor at MIT says, we know, dear, we know. just keep going. Imagine. I mean, it's crazy. This is 1960s, folks. So Nick Percival, who is one of our real, if you haven't, Nick of Time, go to nickoftime.guru. And you can go to his he has a web channel, a YouTube channel, and check it out, Nick of Time. Really great videos. He says he's going to be making some more. Duncan Shaw, who is an etherist, he has what I call the Vancouver ether theory, which he's come up with. And he has made some donations when we have needed. An anonymous a person who donates to us who does want to remain anonymous. I will say it is a male. He is a great guy. And also my father has donated a number of times, like to shut me up because he keeps hearing me ask for donations. And Kurt Renshaw also made a donation, and other people. So if you want to make a donation, it's greatly appreciated. It all goes into our CNPS bank account, and that bank account gets withdrawn monthly and yearly for all the things that we need to do. So CNPS 2002, that is our conference. I know our guest today was got his Lifetime Achievement Award when we were at the University of Washington. I think it may have been the last conference we had. But we are currently accepting papers. You can send an email to proceedings@nationalphilosophy.org. We already have some papers if you want to publish. And yes, you can publish in other places. If you publish someplace that allows you to publish it again, that's no problem with us. We will put it in our publication. The idea is to give our organization, and the official launch of the CMPS conference will be next month, and we'll have more details on that. We had a meeting. If you haven't checked it out, go back. I think a couple of times ago. I can't remember. Go back. One or two, I think maybe it was the last one because we skipped last week as a time off, but I did have a whole session on CMPS 2021, and we had all great inputs from everybody, and I liked a lot of the suggestions. So we're going to be having a meeting with that. If you're interested in helping out, being part of the conference organizations, we're going to be having some Zoom meetings with that, and you can join us for that organization so we can get together the schedule. There are several ways we are looking to do this, but we're going to try to make it so that most people can participate and still have that kind of online get together. And we have some good ideas from that video, and it really wouldn't have happened without everyone's help. So it's going to be taking place in the fall or the end of this year in the Northern Hemisphere, okay? I did live in Brazil for 3 years, and summer was in December. So there you go. The CMPS Publishing, we are publishing 3 books this year. The Not-Finity, Matter and Motion by George Coyne, Consciousness, and of course Big Bang. No, not support of the Big Bang. Absolutely great guy. I hope to have him on once we publish that book. We're going to be publishing sort of all together because we're all sort of he's done with his book, waiting for us to do that. Then we also have Ether, over 400 pages by an anonymous person. He calls himself Ramsey. That's his pen name. And of course, we have Principia Mathematica 2, a complete toolkit for hacking the physical universe. My dad and I took the whole week off, and he and I are finishing up that first version. We're going to get him out to one reader, one of our top people who knows the model first, and then all of those people who have signed up to read it to help us out. No, we're not looking for reviewers. That's going to come. We don't need reviewers, people to tell us we're wrong. We'll have plenty of those people. We're really looking for people to help make our book more readable, more communicate the idea. And yes, Principia Mathematica 2, that's pretty bold, but hey, we didn't give it the title. Somebody else read it and said that's what the title should be. Anyways, if you are wanting to publish, we can help you out. And we even have a format that we've come up with, stealing from the book from Dr. James Maxlow, one of the great, well, in my opinion, the greatest geologists of all time living today. And I like the cover they did for his book. So here's the cover for Not-Finity Process from George. He likes this cover. Here's the one for Principia Mathematica 2, Universe Hack. So those are coming. And I always do this. I have this now in my slideshow so I don't forget. So here we go. We're going to be playing Coming Attractions. Oh, wow. You saw some new stuff in there. You better believe it. What did you see? Well, you saw, of course, we knew this. I've already announced this, the finite theory. Phil Borkert, he is going to be giving a talk on his theory, the finite theory. Nick Percival is working with him so that we can get to that. Also, and I have talked with Steve Bryant, and yes, I think in May, these people, have their own schedules and stuff, but he is definitely on board. He's working on his slides for us. And super articulate guy in presenting, much better than me. He would stand up much better at a corporate meeting than I would, but he is very interesting, engaging, super, super bright. And there is a review of Disruptive, The Demise of Relativity on sciencewoke.org. I think you can check that out. But he's going to be coming and talking about it because I got lots of questions. Great book if you haven't seen it, or take a look at it, read it, and then he'll be on soon. And a new one. Now, this seems a little strange. You're probably wondering why we're going to be talking about Thomas North and Shakespeare. Well, there is some backstory, as we say in Hollywood, with this. The backstory is that Dennis McCarthy was one of the first people to present. He presented actually 2 times, back in 2008 when we started that. Can you believe that? 2021? That's what? 8, 12, 13 years ago when we started these Saturday morning things on Dim Dim. Yep, that's what it was called. And it was Flash. It recorded everything in Flash. Anybody who's a computer person, sorry. Esoteric nerd computer stuff. But he is an expansionist, meaning he has a great talk. I'm going to see if he can come on again because it's been a while, but he talks about the flora and fauna and how in the Pacific you have flowers and animals and all kinds of flora and fauna that are in very strange places that make no sense, that could never cross the ocean or fly. And it turns out that expansion tectonics explains why the coast of this island in the Pacific was against the coast of some place in South America, and those species are only found there. And if they hit the water, like one of them, like the flower, if it hits salt water, it dies. So, anyways, very interesting. But he, again, we look at critical thinking. He has been doing some amazing work with Thomas North, who is a writer who was a contemporary of Shakespeare. And it turns out by using the more modern techniques of looking through ridiculous amounts of text, that it turns out that Shakespeare, in fact, may have used a lot of North's work for his plays. Of course, Shakespeare's super famous. There's the Edward de Vere kind of thing. But anyways, one of the things that we have done, and I'm sort of following this tradition through the CMPS, a person who did this a lot was Domina Spencer. I think she's still alive. She's got to be almost 100 years old, really. She's a vegetarian, lived a long time, but she used to have a few off topics from Critical Thinker. You know, it's always good to have the, how do you say, the soul of critical thinking on your program and on your docket here, so that we can mix it up. It's always physics and mathematics and philosophy and science. So this should be extremely interesting. He has a YouTube channel he just started. You may want to check him out, but he is willing to come on, and I'll get to talk. Maybe we'll talk a little bit about the expansion stuff as well. But that, I'm looking really forward to that. It's, again, critical thinking on a different level, just to break the ice. How do you say? Break the monotony. Not monotony. And guess what? Because of the time changes, and because it's all Dr. James Maxwell's fault, because he's an expansion tech. He was the one who came up with the words expansion tectonics. It's his fault because the Pacific, I blame him for expansion tectonics. So the Pacific expanded, and Australia got on the other side. So it's getting the worst deal when it comes to the best time zone. Because if you start Hawaii, you forget it. Hawaii's unfortunately, but if you start on the west coast of the United States, Australia suffers on the other end, where it's real early for our guest today. It's really late for him, but he goes, "Oh, it's the time change has happened. Can I give another talk?" And of course, Dr. James Maxwell is always welcome to talk. So, hey, and are you next? If you have something you want to talk about, you think, or you know somebody, just contact me, and we have people lining up. I guess the show's becoming more popular, and I want to thank again all you guys watching live and all you people watching this recorded. But we are always open to critical thinking and new stuff. We support everybody who critically thinks out there. We'll take a look at your stuff, and it looks good, we'll put you on. So. And of course, play today's bumper. Okay, well, let me bring this down here. I want to bring on our guest now. We haven't tested anything because he's a busy man, so we're going to bring him online, and hopefully he does enough Zoom meetings. He probably knows all this, so I should be able to bring him up. Hello, Dr. Gerald Pollock. How are you?
Hello, David. I'm great. It's a bit early, as you mentioned, on the West Coast, but I'm here.
All right. Now, you have been, you're at the University of Washington, is that correct?
I am indeed. Well, actually, I'm home mostly. I'm not at the University of Washington, but yes, in theory, University of Washington. Right.
Okay. Now, did you have some slides for us today?
I did. Yes.
Yeah. Okay. And you ready with those then?
I've got them on my screen. I'm accustomed to Zoom, but not this particular.
Yeah, there should be a share button, so I want to let everybody know, so we're going to help with them. There's a share button near the bottom. You should be able to
Here, got it. Should I click it?
Yes, you should. And as soon as I see you get that up there, then I'll let you go.
Share screen.
Right?
Share screen.
You can share screen, or I think you can also share an individual thing like the PowerPoint or whatever it's on.
It's PowerPoint. No, it said open system preferences or deny.
Let's see. That's okay. No, just go ahead and you should be able to share a screen. Now you don't, if you don't have any videos, then you don't have to worry about audio.
Okay, so there's a window that says Google Chrome would like to record this computer's screen. It says.
Oh yeah, you can say yes. I think that's just it's just
Okay,
it's just
got it.
it's just acknowledging that they probably got a lawsuit when somebody didn't know they were being recorded. So okay, so can you share that now?
Well, I got another window that came up that has a lot of stuff about privacy.
Oh my gosh! Well, just keep saying okay with that, I guess.
Let's see. Where do I find? Okay, so I have.
Yeah, it should
Let's
be. It should be that you can. Yeah, if you just hit the share. Normally, when you hit share, it brings up. It says. Let me go. Okay.
Okay.
Try it.
Share. I got
try
it.
Okay. Now, do you see your slides there?
I do.
Okay. Why don't you
says,
choose
it
that?
says share your screen.
Do you have any audio you need?
No, I don't.
Okay. So then just go ahead and click on the one that has a PowerPoint.
Well, let's see where. Yeah, share. Okay. Chrome has lost permission to capture your screen. Follow these steps. Should I put
Yeah.
X on it?
Yeah, I guess so. I
okay.
guess.
Okay. What's next?
Well, it should. Well, it should.
Yeah,
share right
I'm
away.
sorry.
That's okay. That's okay.
Share once more.
Yeah, click it once more. It may be that you're going to have to go through that again. I apologize for everybody. This is the modern world.
See. Share. Whoops. Try
If somebody
again.
knows how to get through this,
Share
then let me know.
screen. Now tips. So let me share screen. Now try again. Share, but
Now
it's
are
not
you
live.
clicking the share button from the window? I mean the window we're in there. There's a share and a mic and all that kind of stuff.
At the bottom? Yes.
Yeah.
That's what
Okay.
I've been doing.
Okay.
Let's see. So then now I have a window. It says share your screen. It says SteamYard.com wants
Yeah.
to share the
Yeah.
contents.
Yes. Go ahead.
So yes,
Yes. Absolutely. Yep.
but I can't. Doesn't do anything when I press share. Should I just try? The other option that's live is cancel.
Yeah. I guess.
All right, let's
Well,
try it.
the other thing is too
Nope,
is
now I'm back to.
yeah. What I can do is perhaps have you email me those, and I can get those and
I'm
put
sorry?
them on my
Have
site.
me-
Can you email me your slides? Send them to David at naturalphilosophy.org, and then I can put them up on my site. Oh, I think we lost him there, or he's. I'm going to bring him down. This happens, folks. I know I did. He didn't have the time to do a session with me, so I'm going to have him. Oh, there he is.
Yeah.
So yeah, if you can just email those to me.
Email what to you?
The slides, and I'll
I
put them
can't.
up.
It's 150 megabytes.
Okay.
There must be a way. I mean, if this has worked before, I'm sorry.
Yeah, I think what's
screwing up
happening is no. It sounds like Google is trying to stop, you from doing it. So you have to go through the Google kind of things. So I guess we just have to sort of go through that if we can. Again, I apologize, everybody. This happens. So go ahead and go through that. And why don't you
try share once more?
Yeah.
Okay, here, share. It tells me now about screen sharing tips, but I don't want that. I'll just okay. Don't show these tips again. I can share screen.
Okay.
Okay, so now I have a window that shows my shows you on the left, and I don't know if it shows my slides, but it says share your screen, and I have choices: your entire screen, application window, Chrome tab. It
Try
looks like
application window. Why don't you try that?
okay. Got
Do you
it.
see your slides there?
I do.
Okay, chose.
Click it. Should
Yep.
I?
Yep.
Doesn't do anything. Um, let's see. Oh yeah, underneath there's Microsoft PowerPoint.
Okay. Okay.
Should I try that?
Yes, absolutely.
I click and nothing happens. Oh, now it says share. Okay, let's see if we can. That didn't do it.
Okay.
Let's see. Maybe
It's okay. It's all
try
right. We'll get
again.
there. Yeah,
Share.
try it again.
It says share screen or video file, and I've been pressing
Yeah, no,
share
yes.
screen.
Share screen. That's right.
Okay,
You
got
can.
it.
That's correct.
So now I have what I have before. I have an image showing you on the left. Yeah,
Try choosing the screen where you have your slides. Do you see a screen? If you click on screen, does one of them have slides?
I don't think so. No, I can't quite tell because it's small, but it might. It has you on the left, and it has something on the right that I having trouble discerning. I don't think it's my slides. No, it's not my slides. No.
Okay, so click on the applications one more time.
Application window.
Yeah.
Okay. And now to the right, it does say Microsoft PowerPoint.
Right.
That's good.
Right.
But I can't. Share is not live. Only cancel. It says share at the bottom, but
Okay.
I can't. If I click it, I don't get anything.
Okay. Okay. I'm just trying to think. I know it's a big thing, but you can still try to email it to me sometimes. Do you use Gmail or do you what kind of mail do you use?
Well, no, it's not Gmail. It's a university system.
Right. It could be that the university system's not allowing the system to happen, if it's depending on what that is. So,
well, I mean, I could put it in Dropbox.
Yeah, you could do that. I think I have Dropbox.
I'm sorry for
No problem. No problem, folks. I mean, we have, don't worry about this. These things happen today and age. There's not anybody who's on here who hasn't been through these kinds of things. And that's why sometimes we need to test them, but no problem. Why don't you try to put that in a Dropbox and then send me the email for that. And
okay,
maybe we can do that.
We'll take a moment.
Okay.
Okay,
All right.
let me get to Dropbox.
All right. I mean, the other thing too is we can have, since some people do know what you're talking about, we can all attend some questions. I know my father's there, so maybe I'm going to have him look at my dad. While you're doing that, I'm going to I'm going to take you down and have you go ahead and go do what you're doing. All right.
Okay, I'll do what I'm doing right now.
Okay.
Yeah, with slides, it's much better. It's
of course,
really hard.
absolutely. Don't worry about it. Don't worry about it.
Let's see. Let me get to Dropbox.
So yeah, we have some questions, but we'll probably get to some of those. But I'm gonna remove him here. But if you have the question again, one of the things we want to do is if you do have questions for us to, let's see if I think I had that before. Here we go. Yeah, if you have a question or comment in the comments that you want to bring to Gerald, Dr. Pollock, please put that as a question, or comment, because I know there's a lot of discussion here, and I appreciate it. And again, I appreciate everybody's patience. Sometimes these things, we've been pretty lucky with it, but sometimes people's systems have some problems. So let me, I'm going to be opening these things up and trying to get his, if you do have questions or comments. But again, we're talking with Dr. Gerald Pollock today. He's going to be talking about the fourth phase of water. Yes, we know the other phases: liquid, solid or ice, gas, and there is a fourth one. And again, if you haven't have seen him talk about those, it's definitely worth your trouble. Let me make sure I have Dropbox here. Yep, there it is, the app. Hello. So we're right now trying to get his slides to us because they are very big. And I'm trying to even get Dropbox on my system here. So, that would be great. Everything's going wrong today. So, let's see. Okay, so again, we are waiting for Dr. Gerald Pollock and sending that, and the Dropbox. I don't see I even have that on my computer. If I do, it's not coming up myself. So it's trying to come up. Oh boy. So the store. Let me go to the store and see what's going on, because my believe it or not, Gerald, my Dropbox doesn't seem to be working myself. So let's go to the Microsoft Store and get this going here. Alrighty, we are silent today. We may just have to go with a I don't know if I can even find, maybe there is some place where we have this talk, some form of talk with that. In fact, we do have another way. We do have another way to do this. Do we have a link for one of your talks that's not too long? Because we're at, let's see, 10:30. We're good. That maybe is about 45 minutes long. Or do you have one of those, Gerald?
Well, I do, but it would be the same problem.
Well, no, I can play it from my end. Was what I'm saying. We could play it from my end, and then we can just use that as your talk.
Well, if you've got something, I could do it.
Yeah.
But we got 3 minutes left here.
3 minutes left for what?
For uploading.
Oh, okay. Yeah, and that's going to take me some time to do that too. So let me see. I'm going to look at this. There is, let me see here. There is one that's 24 minutes long from the TED Talk from Guelph University.
Oh, that's so ancient.
Okay, that's ancient. Okay, well, that's 2013. Yes, it is. Okay, let me look for another one. Water, cells, and life, but I think that's more specific. Water, cells, and life. Got that. The fourth phase of water. That's 4 months ago. That's an hour and 30 minutes though. That's from and the regenerated future.
2 minutes left.
Okay. Yeah. Well, I'm having trouble even with my Dropbox. Believe it or not, it's not coming up. So that's not good. Let me see if I can. I don't know what that means though. My Dropbox is not coming up.
I'm so sorry.
No problem. No problem. Let me look for the video of, let's see, the fourth phase of water. There's one from 3 months ago. Do this to your water. Does the fourth phase of the water beyond solid liquid vapor? And this episode, I interviewed Dr. Gerald Pollock. I've got one from a year ago. Let me see here.
What was the?
Let me try that, because that way you won't even have to do it. Let me see. This one's from. I'm going to move it over here. This one is from the conference on the physics, chemistry, and biology of water. That was done.
I mean that one. Would
that one work okay?
Probably about 50 minutes.
Yeah, that would be ideal. It's 1 hour and 5 minutes. So let's do that. Okay, folks, we're going to do that. Okay. And then
Yeah.
I will go ahead and start that right away. And we
Okay.
will go and we'll be talking with you shortly here then. So let me share my screen. And I apologize, everybody. So screen one, that's this. I'm going to share that. Oops, I've got to stop sharing it. And I've got to get it, make sure it's got video or audio. Sorry about that. Share audio, screen share. There we go. I'm going to make it large here, and away we go. I want, please do thumbs up in the green room if you do hear it. I don't want to start this off and have it so that it's not working. Here we go.
The first speaker, Professor Jerry Pollock. I suppose that many people know who is this person, and I asked Jerry if I should describe his kindergarten years and high school achievements. He said, no, we shouldn't lose so much time because you see the result. The result of kindergarten is here, and he will present the lecture about the fourth phase of water, and I'm looking forward to hear about update what happened during the last couple of years with this fourth phase of water. You're welcome.
Thank you, Vladimir, for your warm welcome. Well, so at first I decided to speak fully on updates, and then I realized that there are so many new people here who are perhaps not familiar with the background. And also, since there are other presentations that will deal with EZ water, I thought I would start with a few of the basics and then interweave some of the newer developments. So some old, some new. And I start with the inspiration that I received, and it came from this same Gilbert Ling. And Gilbert Ling was a controversial guy who came from China, selected among many candidates from China to come to the US to study. He was in the first cohort. They chose three, a biologist, a physicist, and a chemist, and Gilbert was the biologist, or was he the chemist? I'm not sure. These were three distinguished people, one of them, the physicist, going on to win a Nobel Prize in physics, and yet they all thought that Gilbert was the most clever of the three people. Clever but controversial. He came to challenge some of the widely held precepts in biology. And in particular, he was interested in the water because he thought water was really important. And from his experiments, of which there were many, he came to the conclusion that the water inside the cell was structured or organized. That is, there are many surfaces inside the cell, and next to each one of the surfaces, the water molecules took on a kind of order. And because essentially all of the water inside the cell was interfacial water, it turns out that essentially all the water inside the cell was structured. Well, he had a great influence on me, although we never really were you might say, friends, but a great influence. And one of the problems with Gilbert Ling's presentations is they're not easy to digest. And many people who have looked at his books and tried to read them have had real difficulty. It was really clear he had something interesting and important to say. And I gave his books to some of my students, and every one of them said, this is really amazing stuff. He's on to something truly important. So I decided to take it upon myself to make his ideas known to the rest of the world because I thought they were important. And I did so in this book, which has a pretty cover. And the book went on to go beyond Gilbert Ling. The book suggested that not only is the water inside the cell structured or organized, but that the transition between structured, the dynamic transition between structured and unstructured water is a trigger for so many important biological events, ranging from the triggering of muscle contraction to the onset of mitosis to countless issues. So the book turned out, despite the beautiful cover, to be controversial. Some people hated it, and they said, oh, this is Gilbert Ling-based nonsense. and other people loved it. But I have to say that among the more discerning of readers, it was very popular. Chosen from among all other books. Okay, so the central theme of Gilbert's idea is shown here. Inside the cell, we have many proteins and other macromolecules, and the surfaces of these proteins contain a lot of charge. And sitting next to water molecules, shown here as dipoles, that is plus, minus, these dipoles. And physical chemists will argue that because of these charges and because the water is a dipole, you may easily have one or two layers of ordered water. And Gilbert said, no, that's not true. You have many, many layers of ordered water extending way beyond the 2 or 3, maybe dozens, if not hundreds, of molecular layers of water. And I'm going to show you later that the number of layers could extend way beyond even what Gilbert Ling had suggested. Well, we had real interest in pursuing this experimentally, even though I had been in the field of muscle contraction, but this seemed more important than muscles. It was so central to virtually everything. So we had a clue about finding a proper experimental model. And the clue is that when the water molecules are ordered in some way, just like ice, when ice forms, as it forms, it excludes solutes. Otherwise, you don't have a pure crystal, you see. So we were looking for an experimental model which showed exclusion of solutes or particles and such. And by good fortune, we found one easily right away because of a chance meeting with a Japanese scientist. And so this shows what the model is. Inside a chamber, you see here, we put a gel. We started with polyvinyl alcohol. We put it into the chamber, and here's the boundary of the gel. And next to the gel, we poured some water and particles. And the particles are little spheres called microspheres. And what we immediately noticed looking in the microscope is that there was a region here where the microspheres were excluded. We kept seeing this again and again, thinking that maybe, at that point we had no evidence, maybe this was a region where the water molecules were ordered. So it seemed like a promising experimental model. Well, we found it so regularly that an Australian colleague suggested to us we should give it a name. We didn't know that someone else had published this in 1970, some physiologist. And he said, why don't you call it exclusion zone, because it's easy to remember. It doesn't work so well in Europe because it's EZ. But for us dumb Americans, it's easy to remember. So we noticed, though, that with time, this became more dramatic, that this thing seemed to grow over time. I'm showing you about 5 minutes worth. And the microspheres were progressively excluded. The zone grew, and here you can see a zone that's about 50 micrometers, which is really a large zone. So we were curious, naturally, to see whether we would see this zone in other materials. And one material that we came to use quite frequently is naphion. Naphion is much like Teflon. It has the same backbone, but it contains charged sulfonate groups. So it comes in sheets. If you got the money, you can buy a sheet. And of course, you want to conserve, so you cut out a little piece of the sheet. And here you can see we cut it here into an arrowhead shape, plunk it down at the bottom of the chamber, pour in the water and the microspheres, and this is what you see. Same as previous, except that the size of this can be up to 0.5 millimeter. You don't even need a microscope to see it. You can just look at it and see it. So this turned out to be a convenient experimental specimen. So in terms of generality of this, we found many kinds of material surfaces could generate this. Not every one, but many of them, including gels. Every hydrogel we tested, there must be more than a dozen by now, show this. Polymers, no hydrophobic polymers would do this, but hydrophilic polymers, many of them show this, not all. Biological surfaces, every one we examined shows this exclusion zone next to it, and single layers, single molecular layers on gold, standard preparation, when suitably functionalized, show this on a regular basis. So in terms of the surfaces that can generate this, it's quite common. What's excluded? We went down the range from big particles to small particles to big molecules to single-celled organisms, bacteria, viruses, large molecules, proteins, and such, down to about 100 molecular weight and lower. So many hydrophilic surfaces generate these exclusion zones, and many solutes are excluded. We then began studying the physical characteristics. I've alluded to the possibility that this zone may have to do with the ordering of water, but I presented no evidence. So I'm going to list the evidence. There are 8 pieces of the evidence. By now there are more, but I don't want to bore you with this. And I'm just going to mention them because most of it is published, and anybody who wants to look at it, and it's mostly not new. We found the molecules were more constrained using nuclear magnetic resonance, that the molecules are more stable than ordinary water. And this was a surprise for us that the EZ has negative charge, and I'll go back to that one in a moment because this is really important. It absorbs light at 270 nanometers. It's more viscous, sort of like as viscous, it can be as viscous as honey. The molecules are aligned. The molecular structure is not like the molecular structure of ordinary water. And the refractive index is higher, measured by 2 Russians, up to 11% is what they both found higher. So what about this negative charge? And how did we find that it has negative charge? Well, here's a preparation that we used. So this is a piece of Nafion sitting here. It's sitting next to water. And the water contains a pH-sensitive dye. So these dyes are like the dye, remember litmus paper? You stick it in the water, it changes color. This is the same chemicals in soluble form. You can just put in water and you can get these beautiful rainbow patterns of color, which I'll get back to in a moment. So the first point, before I get to the negative charge, the first point is that you don't see any dye in here. This is clear in the exclusion zone next to the Nafion. And so it suggests that whatever molecules make up this dye don't get into the exclusion zone. And usually these dyes consist of 4 or 5 different molecules, molecular weight roughly on the order of 100 or so. They don't get in. So what about the electrical potential? Well, to measure electrical potential, you need 2 electrodes, not 1, to measure a potential difference. So we use these electrodes that come to a fine tip, invented, parenthetically, by Gilbert Ling, for which he should have gotten a Nobel Prize, but he was too controversial to get a Nobel Prize. This was revolutionary because it allowed you to measure the electrical potential inside of a cell, which couldn't be done before that. So they taper down to a micron or less in the tip. So we put one of them as a reference electrode somewhere out here, and the other one in the exclusion zone, and we found regularly negative charge in there. Electrical potential that could be as big as minus 200 millivolts or so. So it was a real surprise because we didn't expect this. We expected neutrality. When you think about it, what you're doing is you're taking some water, which is neutral, and pouring it into the chamber. How can you start with something that's neutral and get a big region that has negative charge? It doesn't seem. So the only way that we could think that this was rational is if the water molecule itself was getting broken up. That is, the water molecule consists of H plus OH minus, and if somehow somehow the molecule would split, then it's possible that the negative parts could somehow gather here to form the EZ, and then we'd expect positive parts out here. This is not a wildly irrational idea, because some of you who know about photosynthesis in green plants know that the first step in the photosynthetic process is the breaking of water molecules into H plus and OH minus. So there's plenty of precedent for this idea. So we thought, if this is really happening, that the water molecules are breaking and the negatives are here, there must be some positives out here. And you've already seen the evidence for this, because this dye, the orange-red color, means pH of 3 or less, which means that this is full of protons here. So because of that, we understood that the positives and negatives were being separated. And just to make sure that we were not deluding ourselves into thinking something that we liked, but that's not really true. Parenthetically, it's said that only artists love their models more than scientists. So we have to be a bit careful. So we stuck an electrode in here, an electrode in here, with a resistor in between. And if there really is this separation of charge, then we expect current to flow from here to here. And here's one of the earliest records showing current versus time. You can see it starts at a high value and it goes down to a plateau. But this plateau is not zero, so current keeps flowing for an appreciable amount of time, which gave us confidence that we were right, that there's a splitting of the water molecules, just like the first step of photosynthesis, between minus and plus. So we felt confirmed that really there was this kind of charge separation. So we have essentially a charged battery in water. So where are we so far? We have, next to hydrophilic surfaces, we have water molecules that are somehow lined up into a liquid crystal. This region typically has negative charge. It excludes solutes profoundly. And some of the evidence that I showed you hints that this dipole model might be wrong. Maybe some of you could already see it, but I'll get back to that in a moment, why this nice, simple model can't be correct. And this ordering of water molecules may extend very far. So how far is very far? Well, if you do the arithmetic, if each molecular layer is about 1/3 of a nanometer, then the size of the exclusion zone that we see means we're talking millions, up to millions of molecular layers. It was suggested more than 100 years ago that water has a fourth phase. Sir William Hardy was a distinguished physical chemist, colloid chemist, and he said, there are too many anomalies associated with water, things that you can't explain with the idea of solid liquid vapor. There must be a fourth phase of water. So I'm not sure whether what we discovered is what he had in mind. It's a little bit too late to ask him, but it may be. And I just want to point out that the idea of another phase of water is not at all a radical idea. It's an old idea. So what I've shown you is nothing new, except that we have some additional evidence. Now, why am I suggesting that we're not dealing with dipoles? Well, it's actually very simple. Even I can understand it. So the reason is that we measure negative charge in the EZ typically. A dipole is neutral. It's got plus, minus, so it has zero charge. So if you take dipoles and stack them from here to Pluto, you still never get negative charge. So we had to admit by this very simple reasoning that the model can't be right, even though it's so pretty. And the model we came up with, and I'm going to skip, to save time, I'm going to skip the rationale for coming to this conclusion. It looks like this. It's a hexagonal sheet-like structure. It starts with a material, a hydrophilic material, next to water, and from this water build one layer at a time, 1, 2, 3, 4 layers that look like this, and they build one at a time. And if you look at the structure, the planar structure, it's a honeycomb structure, which we see so often in nature. And and these are the oxygens and the hydrogens, and if you count in one unit cell, if you count the number of oxygens and the number of hydrogens, you find that it's not H2O anymore. It's actually H3O2. If you think about it, it can't be H2O because H2O is neutral. This region is negatively charged. So, and H3O2 is negatively charged because to achieve neutrality, you need H4O2. That would be double this, and that would be neutral. So the EZ is then is a liquid crystalline structure. And a question that arises, since liquid crystalline structures can often form solids at room temperature, question arises, can the EZ form a solid at room temperature? This is a kind of water, and nobody expects water to be a solid at room temperature, but can it be solidified? So there's plenty of evidence or example. This is a sugar solution, and it was demonstrated that this is a liquid crystal. I think it was Louis Pasteur who, looking at the optical properties, demonstrated that this can be a liquid crystal. And if you wait long enough, out of this emerges a solid crystal, which actually, rock candy tastes quite good. And perhaps you enjoyed that as a kid. It's basically a sugar crystal, a solid at room temperature. So a question that arises is, can you do the same thing with EZ water? And the person who demonstrated that you can do that is sitting in our audience back there, Vittorio Elia. And 3 or 4 years ago, he and his colleagues demonstrated, and his wife Elena, who did most of the hands-on work and sitting right next to him, demonstrated, this is an absolute breakthrough in science as far as I'm concerned. And the way they did it is to take a sheet of Nafion and put some water on the sheet, then an EZ build, and use a roller to roll off the EZ, and also inevitably it contained a little bit of ordinary water. And if they did this and repeated it enough times, and put it in a beaker, they got something that looks like this, where this is presumably the free water, and this cloud-like structure is the EZ. The EZ is coming together to form a large one, and I think it's no surprise and no coincidence that this looks just like the clouds that we see up there, because I believe those clouds also contain a lot of EZ water. Anyway, to construct the solid, they put the water they collected into a lyophilizer, which draws, it's a common technique used by protein biochemists to draw off the free water, and what they found left is a solid at room temperature. Imagine solid water of some kind at room temperature. It's stunning. We repeated the experiment, and this is the result of one experiment. We didn't get too much of it, but you can see the solid EZ water at room temperature. It's a kind of brownish gold. It feels like a strand or a thread of cotton wound loosely and such. And just to check to see if this really was EZ water, if you remember along the list of evidences that I showed, is the absorption near 270 nanometers. And so we checked that. We put this solid EZ into water, and indeed we found, actually here it was 280 nanometers, an absorption at just the wavelength that we expected, which we think is good evidence of the presence of EZ. So our experiments are just beginning, and we plan to do many more, but we're very happy to be able to confirm the experiments done by Vittorio Elia and colleagues. The next question is, could EZ water contain memory? Well, when we think of memory, we think of a thumb drive, like this. And so the first question is, well, how does this store information? I think many of you know better than I do how it does. And typically inside, you have silicon atoms that are arrayed in a regular, not two-dimensional lattice, but 3 dimensions. And each one can be addressed separately. And through a rather complicated mechanism, which I think is not really fully understood, the silicon can take on either of 2 states, which we assign a 0 or a 1. So each one of these has 2 possible states. Now, if you compare this standard computer memory with EZ, if you look at the structure, we have pretty much the same structure. If you look at the oxygens, which exist at each of these vertices, they're regularly arrayed in these 2 dimensions and also in the 3rd dimension. So you have a lot of oxygens sitting in a regular array. And the question is it possible that if you apply electromagnetic waves or subtle energies or whatever, that these energies could impact specific oxygen atoms to occupy one state or another? Now, what's really interesting is that oxygen has not 2 states, but actually 5 different states, 5 oxidation states. So it means either -2 is what we are familiar with, but also if you read any chemistry book, you have not only -2, -1, 0, +1, and +2. It means it means that each one of these has not 2 states, but 5 different states. And if you do the arithmetic, it turns out that the possible information density in one of this is, I forget the number, but something like 10 to the 8th or 10 to the 9th times the information storage capacity of an ordinary digital memory. So huge information storage capacity, and since we have this water inside our body, it means that our bodies should be capable of storing enormous amounts of information. And a question that arises, of course, is will information storage in EZ water, particularly solid EZ water, replace conventional information storage? Well, perhaps the most famous person who had been looking into information or subtle energy or intention storage is Masaru Emoto. 2 of whose followers you heard this morning. And typically what he was doing, the kinds of experiments he did, was to either play music, for example, Mozart, to the water, and then freeze the water and obtain crystals. And John Lennon and such, and either he would think of the word peace or thank you, and he could get beautiful crystals. On the other hand, if he said, I think this means you fool, or heavy metal music, then he would get ugly crystals. Many scientists doubt this, but anyway, you can make your own judgment. And here, right after Fukushima, when the water was full of radioactivity, he came to bring his prayers and his intention to water to clear it. And many people are now following from Emoto sensei, and 2 of them you heard a moment ago. So the answer to question number 2, is EZ physically distinct from the bulk? The answer is yes. I presented a list of evidence, and by now the list can be extended by another half-dozen pieces of evidence, including that you can solidify it at room temperature. And at best, we understand it's a layered honeycomb structure with information storage capability. Okay, so question number 3 is, what charges the water battery? I know that some of you know the answer, but some of you maybe don't. And we struggled for several years to figure out, you know, if you start with chaos and you bring order from chaos, you need to supply energy to do that. It's a fundamental thermodynamic principle. And it took us a few years to find out that, in fact, the energy comes from light. We simply couldn't imagine that. But anyway, if you come back to plants, plants get their energy from light, so it's not so astounding that it comes from light. And it was a student in the laboratory who did a chance experiment who led us to this. We didn't just invent it. He called me over to show me what he had. He took a lamp and he shined it on the chamber in which he was doing one of the standard experiments. This is a piece of Naphion. Here is the exclusion zone and the microspheres. And where he showed me, where the lamp was shining, the exclusion zone had grown by quite a bit. And I suggested to him, take away the lamp. So he took away the lamp, and this thing began to collapse. It took tens of seconds to come back to the same. So it was fully reversible. And, it didn't take a lot of imagination to conclude that, well, where you're shining the light, it gets bigger. And so maybe light, or photons, energy is responsible for building the EZ. We did detailed studies of wavelengths ranging from UV to visible to infrared, and we found that the most effective wavelengths were in the infrared. But where does infrared come from? It's all over the place. If we were to turn off all the lights here and take out an infrared camera, that is a sensor that's sensitive to infrared instead of visible light, we'd see everything. We'd be seeing your badge, your clothing, beautifully. And so, of course, it's used as a night light. You can observe images in the dark, and it has military applications. So it's always there. You can't get rid of it. This energy that's useful for building the EZ is always present. And so if you have a hydrophilic material sitting next to water, the right hydrophilic material, you always will have some EZ. And if you add more infrared, then the EZ will grow bigger. Or if you take it away, it'll grow smaller, back to its original. So the answer to the fourth question about energy is EZ buildup is powered by light, which orders the water and charges the water battery. So it's a very, very simple operation. All you need to do is lie in the sun and your battery gets charged. And so the way to think about this is this water is receiving energy from the environment always. We don't think of it that way, but the evidence shows that this is the case. So now, if this is receiving energy from the environment, the next logical question, if you're awake and not jet lagged, is, well, if this is receiving energy, maybe you can capture some of this energy. Now, my guess is that no one of you has ever seen a glass of water doing work, or am I wrong? Okay, I think not. Well, I'm going to show you that it's possible for this water to actually to do work. And it started with a disobedient student. We found out that Naphion, which we were using very often, comes in tubes. And so we purchased some tubes, and I asked the student to put the tube in the water and see if he can find, with microspheres, and see if he could find an exclusion zone outside and inside. And within a couple of weeks, he had done that. But after that, he kept doing experiments. And one day, he barged into my office, and I was sitting next to some, I think, important visitor. And he comes running in. Usually, this is a Chinese student, and usually the Chinese students are very polite. But he wasn't so polite. He came barging in, and he said to me, I found something that looks very interesting. And so, okay, what's interesting? So he said, I see the water flowing through the tube, and it just keeps flowing through the tube without stopping. And he said, I thought this is really an interesting observation. And I thought, if it's correct, and it turned out he was correct, we checked it. If it's correct, then it means that there must be some energy, because in order to push water through a tube, you need energy. Usually it's pressure that drives it, but there's no pressure gradient here because this point is at the same height as this point. So I thought, if he's right, what this means is that the energy from the environment must be what's driving it, because we couldn't think of anything else. So the experiment looks like this. You pick up the tube, you fill it with some water and microspheres, and you put it into a chamber that has water and microspheres, bring it to the microscope, use a little bit of light to minimize the light, and this is what you see. We had this going for as long as a day and a half without stopping. It just keeps going. We wanted to try some material other than Nafion tubes because maybe this was some crazy feature of Nafion that we didn't understand. And so we created tunnels inside of gels by taking a wire and pulling the wire out, leaving a tunnel as it was gelling. Then we'd have a chunk of gel with a tunnel. We'd put it into water and microspheres. And this is what we saw. So this is a polyacrylic acid gel, and here's the tunnel. And next to the surface of the gel is EZ, and all the microspheres are here. And we got the same result with 8 different gels. The velocity was different. And of course, we were curious to see what happens. We think this is driven by light. And so someone suggested, why don't you just add more light? And so we took up the suggestion and we added more light, and we could increase the speed by 5 times just by increasing the light. So we have a situation with a hollow tube. Work is done because water is flowing through. To do work, you need energy. And so unless someone can think of some other kind of energy transduction mechanism, it looks like the energy absorption inside the water is a necessary condition. So basically the water transduces light energy into mechanical energy. This may seem a little surprising or weird, but remember, the same thing happens in plants. Light energy builds chemical potential in the plant, and the plant then uses this energy for metabolism, for growth, for bending, for whatever. And the results I presented suggest that the same thing happens in water as happens in plants. And it's no surprise because the plant is mostly water. So it means that the water always contains energy. There should be a constant here, I'm sorry, otherwise the units don't match. But I think you see the essence is that this contains energy all the time. We don't think of it as such. So why is this important? I think it could be foundational for any science involving water, molecules, and light, and foundational for health. So with the time I have left, I'm going to talk a little about this. The question is, do we use light energy? So you all know that plants do it, and also some bacteria photosynthesize as well. So he asked the question, if you were Mother Nature and you were quite successful at plants, using energy for plants, and you decided one day, hey, I think I'm going to invent animals. I'm getting a little tired of plants. So you have a couple of choices. One choice is to throw away this transduction mechanism using light and go for a new one. Animals can forage, they can get food, you can use the food to get the energy. So if you're Mother Nature, would you throw away what you got and use successfully, or would you retain it as a backup or as a supplement or whatever? I think being conservative, Mother Nature would probably keep this in reserve for us. We don't think that we use light, but I'd like to suggest to you that we use light, not exactly as plants do, but in kind of much the same way. We receive light all the time. And the first idea that we were thinking of was maybe the cardiovascular system, because there are lots of blood vessels near the surface. And the light penetrates, depending on wavelength, beneath the surface. So who knows, maybe nature is using light to help propel blood in the cardiovascular system. At first I thought, this is very unlikely because I studied the pressure and flow in the cardiovascular system for my PhD. I thought we understood everything. And so when my good friend Vladimir invited me to Moscow University and introduced me to his next door neighbor, who came and said, there's a big problem in the cardiovascular system, I approached this with a little bit of arrogance and doubt. I thought I really knew it all. Within 5 minutes, he had me convinced that there really was a big problem. So what's the big problem? The big problem is that the red blood cells are 6 or 7 micrometers in diameter, and they have to pass through blood vessels, capillaries that in young, healthy adults can be 3 or 4 micrometers in diameter. That is half the diameter. So how does a big, galumphing red blood cell get through a narrow diameter? It looked as though nature had made a mistake, because usually you don't do that. You don't take a football and try to squeeze it through a pipe that's this big. So it turns out, indeed, that this is the way it works. So red blood cells should look like this, but when they go through blood vessels, and you see some blood vessels here in muscle tissue, you can watch the video here. In order to get through, they, whoops, something's supposed to work. They need to bend. So in order to bend, and you can see this guy is having some difficulty. In order to bend, you need to supply energy because you have to squeeze something. I always like to use the analogy. It's sort of like the toilet. Sometimes the toilet won't flush, and you need to take the plunger and push it through, and this takes energy. Multiply that by a gazillion red blood cells, and you come to the conclusion that Vladimir's friends came to, that if the heart were responsible for doing this, the heart would need to develop a pressure that's something like 1,000,000 times the pressure that it actually develops. And these guys said, no way. So they had some other ideas, and I'm starting to think, gee, we just found in the laboratory that we take a tube, put it in water, and we can get spontaneous flow. Is it possible that the same mechanism is used here in nature? So we had this, and the question is, might radiant energy or light help to drive blood flow? And we found support from an Israeli group. Just published a paper. They were studying mice. They were measuring blood flow in response to some drugs, or I can't remember what. And when the experiment was over, they did what experimenters usually do. They sacrificed the mouse, and the mouse died within 10 seconds. The heart stopped beating. But they found they were measuring the flow, and the flow didn't stop. So they were totally puzzled because, of course, when you're dead and the heart stops beating, you shouldn't have any blood flow. But the flow kept going. Reduced velocity, but it kept going. And they waited 5 minutes, 10 minutes, 30 minutes, 60 minutes. Then they repeated the experiment in 10 mice. They got exactly the same results. And they concluded that they were bewildered because something is going on. And my resourceful student found similar results, a half dozen different papers published over the past century or so that came using different models that came to the same conclusion. But of course, these papers are all ignored because everybody knows that it can't happen, that the heart is solely responsible for driving blood flow. Therefore, it can't be true. So we did our own experiments, and the experiments are just completed. So we used a chick embryo 3 days old, and here you can see it. So this is the egg, and we lopped off the surface of the egg, took it off, and you can see the embryo, the vascular system in the embryo developing. And Zheng Li was able to microscopically examine this vein here and another vein here. And the first question was, if you stop the heart, does the flow continue? He stopped the heart just by dropping potassium chloride on it, and he found that the flow continued. So So here's flow versus time. And you can see that the flow diminishes, but it doesn't go to zero. It goes to some plateau value, which actually continues. And then he wanted to test whether our model, the flow in the tube, is what was driving the flow. And the signature feature of this mechanism is that infrared energy is driving it. So if you add more infrared, it should speed up. So he applied infrared, and you can see that the speed increased by about 3 times. And then he removed the infrared, and it went back to the baseline. So we just submitted this for publication. And so we concluded, indeed, that radiant energy does help to drive blood flow. And so it means that if we're right, it means that in your cardiovascular system, it means that it's not just the heart that's driving the flow, but also the blood vessels themselves are assisting the heart in driving the flow. We don't know how much is going on, but and this has important implications, because it means therapeutically, for example, it means, first of all, physiologically, that your metabolism, which is generating heat, the heat is not wasted. The heat is used to drive blood flow. And it means therapeutically that if you were to apply infrared energy from outside, it should help to increase your blood flow. So the question is, what about elsewhere in the body? And I think the answer is yes. It's not just in the cardiovascular system. If you look at, for example, a typical cell, so the cell contains solids, mostly proteins, some nucleic acids and others, and they interface with water. And so this should be easy water and negative charge. And the cell is very crowded. So it's got lots of easy water practically filling the cell, and lots of negative charge. The positive charge goes out. It's free. It's driven out. Positive charges repel each other. So inside the cell, you've got negative charges that repel one another, and that repulsion is potential energy. And I've argued in other places that this potential energy is what drives protein folding. Protein folding is what does the work of the cell. So the situation is something like this, that you have a protein in its extended state with easy water surrounding it, and what happens is the easy water melts, transitions into ordinary water, and then simultaneously the protein folds. And then going back to the quiescent resting situation, the easy water builds back up again, and the protein goes and occupies its extended form. Now, if you don't have easy water, you don't have enough of it, then the protein is impotent. It can't do its job anymore. So basically, potential energy from EZ drives the work of the cell. So to go through the process, light builds EZ, you get negative charge from that, you get energy, potential energy from that, and this energy is used for the work or folding of proteins, the work of the cell. Connecting the dots, light is responsible, or partly responsible, for work or folding of the proteins. So where do we get our energy? Well, of course, particularly in Europe, I just came from Italy, we get our energy from food, and the food is really delicious there. But also, we get energy from light. This is what we don't think about. The light is absorbed by the water, which builds EZ, which gives us energy. So should this matter to you? Yeah, well, water matters, of course we know that, and light matters. And so for your health, the question that you may wish to ask is, what builds EZ water inside your cells? Because you need that EZ water to function properly. And I'm going to give you a list of 6 of them, and these are very common expedients known for many years to be good for health, but nobody really has understood the mechanism, and I think the mechanism may be as simple as just buildup of EZ water. The first is drinking a lot of water, or foods containing water, is the raw material for building EZ water. So we all know we need to drink a lot. The next one is green juicing. So what's that? Well, you take freshly grown plants, you squeeze them. You're squeezing out the water from inside the cell. This is intracellular water. It's filled with EZ. So you're squeezing out the EZ and you're drinking the EZ. And possibly by drinking this EZ water, the EZ water that you've been drinking is used to fill, to replace, to amplify areas where EZ water is missing, where the cells are pathological or ill. Another is various substances that have been known even since Ayurvedic times to be good, generally good for your health. And we studied 7 or 8 of these by now, and just recently published it last year. And we found that they all expand the exclusion zone. So one example is basil or holy basil used. And this is EZ size, and this is concentration. And you can see what happens is that at the low concentrations, which would be common, typical of what we have in the body, the EZ water expands. At high concentrations, almost everything reduces the size of the EZ. We did the same with coconut water, and essentially we got the same result. We also studied fats. You know, fats have been cast in the past as villains. We shouldn't be using fats because they clog our arteries, and the sense has reversed in the past decade or so. Fats are now considered to be good for health. Stay away from sugars. So we wondered whether EZs build next to fats. And here's what we found. This is ghee, cold ghee. You can see a sizable EZ.
Two things I did wrong there. I had my mute on, and then I had the. You'd think after weeks and weeks I'd get this right, but anyways, thank you for making the gesture there. Again, thank you so much. It was really interesting to see some of the history behind of what you do. I mean, I've seen this. I've seen obviously your work for over a decade now, but there's quite a lot of stuff happening more recently, and also finding out what other people have been doing, and some of your research students actually finding what other people have done. I thought it was really interesting that you had mentioned that this whole idea of EZ water and this other form of water was really, I guess, foreshadowed. Would you call it a foreshadowing before you guys really figure out the structure? Were you, I guess what my question would be, were you the ones who found out the actual structure of it, or was that actually found out before you guys?
Well, I think we discovered the actual structure as you point out. You know, for a century or so, there were lots of hints that something is going on that is different from the accepted point of view, and there are a lot of people who had real interest in this. But you know, water used to be something that was studied widely by scientists, and you know, you come to expect that because water is so central for everything in the universe. But it almost stopped dead because of a couple of debacles that took place in the field. A couple of really prominent scientists began studying water, and they found some aspects of water that seemed almost unbelievable. And one of them, the first one, was Boris Deryagin, who was perhaps the most prominent of all Russian physical chemists a generation ago. And Deryagin found some weird properties of water. And at first, it was in the Russian literature, and this was the time when Russian studies began to be translated into English, and once that happened, the Western scientists became aware, and it seemed as though Deryagan was studying something that was kind of equivalent to what we found later, and I think he was onto exactly what we found. And some people call it poly water because the water that they were studying looked like a polymer of water. It had those properties. Anyway, it didn't go very well because some U.S. scientists. This was the time of the Cold War, and the Americans were accustomed to thinking of the Russians as incompetents. Well, of course, the truth is exactly the opposite. The Russians were amazing and still are amazing, but soon after the paper in Science was published by an American group declaring that Deryagan stuff was poly water, other people found, or apparently found, that it was an artifact. It was due to contamination. And at the end, Boris Deryagan recanted. He said, "You guys are right." And that was kind of the end. The truth of the matter is, from what I found out from two people who were very close to Deryagan, they told me independently the same thing. They told me that until he died, he was sure that he was right. However, he was under pressure from the Soviet government to take responsibility for this debacle. Otherwise, the Western response was, "Oh, the Russians, the Soviets, they don't know what they're doing." But now it was Deryagan who didn't know what he was doing after he recanted. So that's one story, and I won't take the time to go deeply into the second story. The second one had to do with the idea of water memory and Jacques Benveniste, whose work has been confirmed multiple times. But again, water memory, this is nonsense. It can't possibly happen. And so those two debacles had a serious impact on the field of water research. Basically, it turned out that nobody wanted to study water anymore because they were fearful that these two prominent scientists, if these two prominent scientists could go so far astray, then what about mere mortals like the rest of us? So a lot of people stayed away from water. And I remember when I was a graduate student about to get my degree, a professor who happened to be studying some aspects of water gave me good advice. He said, "Jerry, you can go into anything you want to do, but stay away from water." And I stayed away from water for quite a few years and then happened to get back to it. So,
that's quite amazing. I think what we're going to need to do is have you back if you don't get traumatized by the 7 a.m. wake up time. But I mean, we had a discussion that at our conference about, and that's a whole different subject. We're going to stick to the water today. But I mean, it seems, I've said this to you before, and I've said it to people in our group. I mean, it's one thing to say relativity and Einstein's wrong, right? It's one thing to say the Big Bang's wrong and that dark energy doesn't exist or that the Earth's expanding. Those things can, you can see the controversy that it may, bring, even though in our sense, if you're a critical thinker and you look at it, just like what you were doing, you say, wait, you can say what you want, but relativity doesn't work. The Big Bang has all these problems, et cetera, et cetera. Expansion tectonics is way better, et cetera. But, water? I mean, you'd think that it's not like you are making up a system, for instance, like quarks, where they make up stuff all the time in particle physics. And no, you can't check it. No one can check it. So you can check this. If somebody wants to, they can take easy water, right? Put it to the test chemically, and they can see sheets of hexagonal sheets of molecules. I mean, of atoms, right? I mean, why? That's a whole nother thing. To me, it's really amazing. So let's get to some of the questions here. I know, especially a part of this is the health. I mean, I've been on an whole plant-based diet for 9 years. I reversed my heart disease. My arthritis is gone. I was told that the capillaries, everything's opened up. My cholesterol is normal. But one of the things is interesting, I've got a question here, is what might be the relationship of water and consciousness? I guess that would be more in the brain. Have you done any work where because there's the regular cells, and of course neurons are a whole different story. Have you done anything with the neural side of it at all?
Well, your question is a complicated one,
Yes.
and starting with the consciousness idea. I used to be a kind of nuts and bolts guy, and the idea of consciousness was a kind of strange, but I've come to change my mind about that because I've seen so much evidence, and in particular the idea that we can exchange subtle energies. In fact, I right now at this very moment, unfortunately, I've got a wrenched back, and I've got remote healers that are now working on a daily basis. One of them is a famous Chinese healer, Master Sha, who is helping me to recover from this. And there are daily remote healing sessions. And, this is the kind of thing that is at the center of consciousness. How is it possible that a healer from a remote location can possibly influence me? Well, there's a lot of evidence that supports this, and this is presented at our annual conference on the physics, chemistry, and biology of water, from which this video came originally. And this has gone on now for 15 years. And at the conference, there are invariably 2, 3, 4 presenters who are talking about how the water is able to store information and yield information as well. And I think the basis of that is, as I was presenting, is the easy water, because it, just like a computer memory, it has the capacity to store information. And so your question about consciousness, it's so tied up with water, and the problem is we don't understand that this is in my view, a frontier topic. It's going to be discussed more and more, but something is going on there. It's not possible to simply dismiss it because there's too much evidence. Even Luc Montagnier, Nobel laureate, discovered HIV, and he's studying water and information storage in water, and his evidence is astounding. Evidence that even DNA, or the water surrounding the DNA, can actually send information and be received by water. And others dealing with remote healing, remote. And we have some experiments that are about to begin in our own laboratory looking at water. So the idea is to have a so-called healer, people who have the capacity to basically to heal, sit down next to the water, send their influence to the water, and then we check the water before and after using, we have 5 different physical measurement techniques in our laboratory that we're about to apply. And so these experiments are about to begin. We're just doing a checkout of the system to make sure everything is working properly. So yes, water, information, consciousness, I think they're all tied up, and I do believe that easy water may be central to all of this capability.
Okay, there was another, I had this up here. Do you have, somebody asked, same person said, do you have a historian working on the history and memory of your laboratory? Meaning, are you guys putting this down, sort of documenting your work, meaning,
we're not so important as to have a historian. But
not yet.
I'm flattered by your interest, but we got a website, and some ideas are presented on the website, and basically
is that pollacklab.org?
Yeah, PollockLab.
Okay, I put that up for people right now so they can see. Yeah, so go ahead and tell us a little bit about that.
It's not a complete history, but I think my book is it's called The Fourth Phase of Water, and it's become exceedingly popular, and with wonderful reviews. I'm flattered by the reviews, and A lot of people get that. That describes it describes essentially all the evidence, or most of the evidence, up to about 5 years ago when it was 6 years ago when it was published. I recommend it because not only because it describes the science, but because the artwork is terrific. So many people have commented, and the artwork is done by my son, Ethan. Oh, there you go. Thank you. Who's got cartoons in it and beautiful diagrams, and he's tremendously gifted. And so it's my great pleasure that he has interest in doing the artwork that for his father. And
Right.
yeah.
Yeah, it's a great book. Yeah, you should check it out. Actually, there's quite a few. Let me see here. I've got some stuff that, here you go. If you want to check out Dr. Pollock, he's got a number of books here. I guess you have, of course, the staple one, which is the basics of the fourth phase of water. Then you also have, I see there's water in the cell, the cells, gels, and the engines of life, which one you talked about just in the video.
Yeah.
So those are really the two main ones I think people should look at.
Correct.
Yeah. So those, if you go on to Amazon, they're there. So I think that's something people can do, or they can check out your website as well. We have the green room, which are people in the green room. I don't know if anybody there would like to. Okay, I'll bring somebody up here. Hello there. This is Bob Gray. Welcome, Bob.
Hello.
Hi, Bob.
You. Thank you for the presentation. For the water that flows through the tubes, do you know what determines the direction of the flow?
Good question.
It seems symmetrical to me, but there's a certain direction somehow.
Yeah, well, I think you put your finger on it. I think there has to be some asymmetry to start with, and we find, I didn't mention it, but we find in 10 or 15% of experiments there's no flow, and we presume in those cases that the system is symmetrical. And how do you create asymmetry? Well, first of all, the preparation itself is I diagrammed it as a cylinder, but of course it's not a cylinder. It comes the tubing comes in long rolls, and you cut off a segment, and as you cut it, if you look under the microscope at each edge, it's frayed. It's actually oval. It's not, because you've compressed it. It's no longer circular cross section, and also light. So since light is critically involved in all of this, if you're sitting near a window and more light is coming in from the right side than the left side, then you're creating some asymmetry. And so those are probably factors that matter. We did some experiments. We created a tapered tube, thinking, maybe we can figure out something about direction. And we found a consistent result that the flow came out of, the first experiment. It was either the narrow side or the expanded side. And then a student came and did the same experiment in using a different gel, and he got the opposite result. So we thought we had something, but we didn't have it. Yeah. So the short answer is, we don't know. However, we believe that some asymmetry must be involved. I'm sorry, I can't give you a better answer.
I thought I read someplace that in arteries, that the interior wall is actually rifled.
Rifled?
Rifled. Sure. There's a spiraling groove or aspect to it, and didn't know if there might be something there as well to. Anyway.
Well, yeah, the flow is actually spiral. When the flow comes out of the heart, it's got a twist to it, and some people have argued that as a result of this, that the heart is not a pump. I'm not sure I agree with it. I see their point, but it does develop pressure, so I think there is a kind of pumping action, but people have taken into account this spiraling effect and think that it may be very important. One thing I should mention, though, is that inside of blood vessels, this is old work, 60, 70 years ago, people noticed that there was what we call an exclusion zone right next to the arterial or capillary, or I forget which vessels, but there's a zone where the red blood cells don't want to go. And so now we would interpret this as an exclusion zone where they don't want to go. And we actually did some experiments long ago, not published, where we actually opened up a vessel and we exposed it to red blood cells. And the red blood cells didn't want to go near the surface. So we think that that is evidence of an exclusion zone existing just inside the vessel wall.
Curious.
So it kind of comes together finally. Yeah.
Thank you.
Sure.
Thank you.
Pleasure.
Okay. So anybody else in the green room want to make a comment or say hello? Oh, I do have another person. Hello there, Dennis. Are you there?
Yes, I'm here. Thank you. You say that the water is influenced by light. Easy water, I believe you called it.
Yeah.
It's now known that besides the usual transverse radiation light, excuse me, there's also longitudinal wave type light, which is said to play a big part in nuclear explosions, for example, nuclear bombs, which most of the radiation is believed by some people to be actually longitudinal rather than transverse, which is the usual type. And this may explain why the sun, according to instruments, astronomers' instruments, the sun is just a dot in the sky, but if you look at it, it's bigger than the moon even. And but the instruments are detecting transverse radiation, not longitudinal. So I thought I'd mention that since you had brought up several times about how important light was to your theories of the fourth phase of water.
I'm not sure what your question is.
Well, I think it has to do with Gerald. He's talking about that light comes in different types of waveforms.
Yeah.
And maybe that one, I know you talked about, it's really just the infrared seems to be, I think from what I can say, from what I glean from your work, it's more of where on the spectrum has more effect than what type of wave form it is. I don't think that's something you've looked at yet.
Exactly. We've not looked at it. I mean,
Yeah,
basically, we've taken an infrared source
Right.
and using LEDs, so we don't attempt to distinguish any between the various modes of light. I'm aware of the theory about light and the different forms, but we've not studied it.
Right. Okay. Any other question, Dennis?
No, I just was, it wasn't really a question. I was just trying to inform him that
Right.
they look at it in the direction of longitudinal radiation.
Right.
If transverse radiation theories don't quite work out.
Right.
Well, do you know of an experimental approach to distinguish between the two?
If you give me your email address, I'll send you a copy of a paper by Monstein and Wesley.
Okay, well, we can do that. And you can go to his website at pollacklab.org, right?
I'm not sure of the URL exactly, but that will get you there.
Yeah.
It's okay.
You have contact information on pollacklab.org, right?
Yeah, I do.
Yeah, okay. So that you can go there, Dennis, and find that out. Okay?
Pollacklab.org. Okay.
Yeah, it's calculated. Okay? All right, thank you very much. How about anybody else in the green room want to say anything? Okay, Ian, I have Ian Cohen, who is from Ireland. And by the way, did you guys have Wednesday off, or is that American bastardization of a holiday?
Well, no. We do have that day off, but every day is the same to me now. I'm retired, so.
Oh yeah, rub it in.
Other day.
Okay, go ahead.
But thank you. I'm just wondering, it's just a particular point, whether this fourth phase has any bearing at all on the anomalous expansion of water. You know, at 4 degrees Celsius, it expands in both directions. So between 4 and 0, it's actually expanding. Is there any relationship in what you've been doing to this?
Yeah, well, I think it is. There is. It is described in more detail in that book, in the fourth phase of water. But what we found experimentally, you know, if you want to freeze water, the usual interpretation is you go from liquid water to ice. But we found that's not true. We found that, in fact, if you want to freeze water, you go from liquid water to EZ and then to ice. See, and so you need to look at the density of EZ in order to answer your question. And EZ is very dense. It's the densest state, and so. So as you reduce the temperature of the water, you go through the EZ state, and then EZ, it's getting denser and denser as you cool it, and then ice, of course, is much less dense, and so when you transition from the EZ to the ice, you get an expansion. That's why, of course, ice floats. So I think the answer to your question lies in the fact that you don't go from liquid water to ice. You go from liquid water to EZ, which at perhaps roughly 4 degrees. It's not as precise as we think, but roughly. And then the transition at 4 degrees from roughly 4 degrees from EZ to ice, which expands. And I think that's what perhaps explains those density features to which you allude.
Okay. Did you have any other comments, Ian?
Well, just a subsidiary. Have you any sort of rough figure as to what the density of EZ is? I mean, is it multiple times that of water?
No. It's just slightly higher. And if you look at the molecular structure, you know, you have these sheets. You have one sheet that's fairly densely packed, and then you've got another sheet that sits right on top of that. And this sheet-like anatomy, if you will, or structure, is very dense. Everything is packed so closely together, and so from this molecular structure, you can intuit that it must be pretty dense. And we have some evidence for that. We have a chamber in which EZ is growing at the edges of the chamber, and gradually it sort of slides down to the bottom, suggesting that it's indeed denser than liquid water. So from those two, from the observations and also from the molecular structure, you expect it to be more dense.
Okay.
Okay, thank you very much.
Okay, thank you very much, Ian.
Sure.
So one other question about the EZ that I have is you have the layers. Now, are those layers, because of their polarity, always sort of fall together in a certain way, that they stack in a certain way?
Yeah, they have to. They can't stack in alignment, because if they were aligned, then you'd have positive next to positive and negative next to negative. And so what we found is they shift.
Right.
There's a displacement which allows the negatives on the lower one to line up with the positives on the next layer, so they stick together.
Does it form a repeating pattern at any time?
It does, yeah, and it repeats. Each layer is shifted by half of the oxygen distance in one plane. Yeah, so the planes could actually line up in a progressively staggered way.
I see.
Yeah.
Okay, and another question. You were talking about clouds. Is it the case, because it was really interesting, I thought, that where they actually squeegeed off easy water, right, into this cloud and put it into the solution, and you could see it, and your comment was it looked just like a cloud. We're going to have to be going, but maybe for the last comment is, obviously we human beings look at clouds. Clouds are really important emotional psyche thing that we living on Earth see all the time. Yet the truth of the matter is, we all think of that as maybe gas. What is it? I mean, because is it steam? It's not steam because it's got to be a certain temperature. So, what can you say with your work with water, easy water, this fourth phase of water, about quickly? We don't have a lot of time, but about the clouds. How is that? Is that all easy water? Is it some? What's going on there?
I think the clouds are built of little droplets. We call them vesicles because we don't know if there's water or vapor inside of them. And each one of these has an easy shell. So the evidence that we gather, and this will actually appear in my forthcoming book about the role of charge in the universe, if you will. The clouds consist of little droplets that are held some distance apart from one another. If these droplets merged, then it would be like climbing up to a cloud level with a pail of water and turning, and it would come right down like a waterfall, but the clouds don't do that. And so the evidence that we have is the clouds consist of little droplets that are held at some distance from one another. It's like a colloid crystal. Too much to explain, without a couple of slides. And it contains these droplets are actually negatively charged because of the easy shell, which is negatively charged, which exceeds the positive charge inside. And the reason they're suspended up there is because the Earth has negative charge and the cloud has negative charge, and they repel one another. Right. And that's why you can see sometimes stacks of clouds, because of the difference of negative charge. So I think, you hit on a good point, and the reason the clouds are suspended instead of not suspended is exactly that. A negative electrical charge repels the negative charge of the Earth. Right. Okay. So I know we're out of time, so I'll stop.
No problem. I know there's anybody in the green room have a quick comment. I know you some people in the green room. I think we're good. No, everybody, no waving. So, well, listen, I want to thank you so much. Don't worry about the snafu of the slides or anything like that. Today and age, if anybody who works online, like most all of us do, my boss is in Cork, Ireland, for goodness sakes. We know that things can go wrong sometimes, but I really want to take time to thank you so much for first of all, your work. You are an award winner, a Lifetime Achievement Award winner, at least from our organization, small as it is. But it's just stellar work. It's wonderful for you to take the time out and tell us a little bit about you've got a book coming out soon, is what you're saying?
As soon as my son can finish the artwork, he's busy remodeling his home, and that takes precedence.
Yeah, so of course. Life gets in the way.
Yeah, the book deals with the role of charge in nature, and the argument is that charge-based forces, are so dominant that we've perhaps come to ignore how important they really are in so many aspects of nature, starting with the turning of the Earth and the weather, and even perhaps gravitation, and how birds fly, how certain sailboats can sail almost directly into the wind, et cetera, et cetera.
Well, that looks great, and hopefully maybe even this year.
Yeah, I hope so.
Yeah, okay. Well, thank you so much. I'll let you go, and greatly appreciated. And if you want to check out his work again, you can check out on the website. It's at pollacklab.org. Thank you very much, Dr. Pollock. We're going to take it out from here. But,
well, thank you, David. It's and I'm really honored to have received that award from your organization.
Yeah,
thank you very much.
No, you greatly deserve it. Thank you so much.
Thank you. Okay. Take care.
Okay, bye-bye.
Signing off.
Well, again, his work, if this is your first exposure to it, you should definitely get his book on easy water. It is amazing that it took us this long to get to one of the most important, if not the most important substance to life as we know it. That's what we look for on other planets. And yet we didn't even know that there was easy water or sheets of hexagonal H3O2. I believe I got that right. And his work is just phenomenal. So if you haven't checked it out, buy his book. It's only like $20 on Amazon. Should be everybody should read about that who enjoys science. And of course, we're going to take you out, and we got lots of other people coming up in the weeks coming. But let's just run a few of our videos before we head on out. I know we've run over, folks, but it was well worth it. And remember what I always say, stay critical, stay thinking. I'm David D. Hilster. I am your science therapist trying to get you the promised land of becoming a critical thinker. We're not here to tell you what the truth is. We're here to help you get to truth for you. Ciao for now.